Hello and welcome to this video on solving quadratic equations by completing the square. Alright, so in a video prior to this I talked about what it means to complete the square on an expression in one variable, and what we're going to be seeing in this video are quadratic equations in one variable. So that means your polynomials, and the highest power, the highest degree of any of the terms is 2, or a square. And so I'm going to start off by refreshing your memory as to what completing the square is, how do you perform that operation of completing the square, and then how are we going to use it to solve any quadratic equation. And that is the beauty of it, is you can use this method I'm going to show you in this video today to solve any quadratic equation in one variable. Alright, so let me begin. So on this first page, I just wanted to go over a recap of completing the square. Alright, so recall when I was completing the square, I had an expression that looked like the following. Some variable to the second power plus, and then another term with the same variable to the first power, and then some coefficient, right, times some number. So this b here that I have is a real number. And one key, again I put this in my last video, one key was we could only complete the square, or we only desired to complete the square on an expression like this when the lead coefficient, or the number attached to the x squared term, is 1. Okay, so we're gonna try to make that happen in our equations later. Alright, so what we did was we took an expression like this, x squared plus bx, and then added something to it to make a trinomial that was a perfect square trinomial, right? Something that could be factored as the same factor twice. And what you would add was you took the coefficient of x to the first, the little b here. You'd cut that in half, right? So take half of little b divided by 2, or 1/2 times b, and then square that number. So take half of b, half the coefficient of x to the first, and then square it. And in doing so, right, after the addition of that number, you're then going to have what's called a perfect square trinomial. Right, an expression with 3 terms that can be written as a perfect square, right? The same factor twice. So you are going to be factoring then afterwards, right? Factor this thing, and the way it would factor is, again, the same factor twice. This, the same one expression times itself, or one expression squared, and that expression is simply the variable, x, or whatever the variable is. You're going to see in my examples I'm going to have other variables, but you have the variable, and then plus whatever half of that b was, right? That b over 2, or half of b. And this is key right here, okay? And this was called completing the square. I started off with, a variable squared plus a number times that variable to the first, and then we added to it, this half b squared, so that I have a perfect square trinomial and can factor it, rewrite it as a perfect square, the same factor to the second power. Alright, so keeping this in mind, alright, let's talk about how we're going to solve equations using the completing the square method or operation. So in my examples today, I'm asked to do the same instructions. I have solve the equation by completing the square. Alright, so I have now notice, no, it's not x this time. Maybe it'll be a bit confusing. with this first one, but the variable this time is b, right? Little b. All right, so the steps for solving, and again, these are good. This completing the square method. You can use it for any quadratic equation, and that's huge, right? So if yeah, there are some you could solve by factoring or solve by the square root property. Now we're going to eventually use the square root property. That's the whole point of completing the square here, as we're going to see in a second. So the first step is I want to get the equation into the form of that x squared plus some number times x. And I know it might be a bit confusing. This little b is a number, whereas the little b in here is actually the same as the x, right? These are the variables, so try not to confuse those. Equals, and then some number. I'll just use n for number. Okay, that is just some number on the other side. So let's do that here. All right. So what I want to do is I want to get my variable squared with, again, a coefficient of 1 on that square, and then plus another term with the variable to the first power. Get that on its own side, and then everything else on the other side, just the things without variables on the other. All right, so in this example here, I have the variable squared, b squared plus, and then the variable to the first power term, 2b. But this minus 8 I don't want over there. Right? So I'm going to add 8 to both sides. So that gives me what I want. B squared, and notice it is 1b squared, right? The coefficient is 1, plus 2b on the left equals 8 on the right. 0 plus 8. Pardon me. Then complete the square. Now I'm going to warn you here, don't forget that this is an equation. What I mean by this is that, I'm going to complete the square on the b squared plus 2b. Right, so that means, remember what that means? That means we're going to be adding, right? So I have b squared plus 2b on the left here. When I complete the square, right, we're going to be adding a number to this. Right, I'm going to be adding a term to this so that I get a perfect square trinomial. But don't forget it's an equation, right? I have equals, and then on the other side there's an 8. So, whatever I add to this side, don't forget to add it to the other side as well, right? It is an equation. You must keep it balanced. Alright, so remember the steps for completing the square. I have my variable squared, times 1, plus some number times the variable to the first. Remember, you take the number that's multiplied by the variable to the first power. So in this case, that's positive 2. You take half of positive 2, which is positive 1, and then square it. And what's 1 squared? Just 1. So the number 1 gets added to complete the square. All right, again, this is half of 2, but then squared, 1 squared is 1. And then again, don't forget it's an equation. I'm adding 1 on the left side of the equal sign. I must, to keep it balanced, I must also add 1 to the right side. So now I have this. I have b squared plus 2b plus 1, which, since I performed the steps that I should be for completing the square, this should be a perfect square trinomial, right? 3 terms that I can factor as a square. And we're going to do that in a second. And on the other side, 8 plus 1 is 9. Alright, so I've completed the square, and then, part 3, step 3, actually factor the perfect square trinomial that you get after completing the square. So b squared plus 2b plus 1. Remember after completing the square, the way it factors is, it's going to be, I have a perfect square trinomial. It's the same factor twice, or some expression to the second power. And in that expression, in the base on that power of 2, you have your variable, which is b, plus whatever half of that number was that's multiplied by b to the first, right? That's positive 2. Half of positive 2 is positive 1. And you can double check this. Take b plus 1 and square it, right? Take b plus 1 and multiply it by b plus 1 again, and do all the distributing and foiling, combining like terms. You're going to get b squared plus 2b plus 1 back. All right. Then I have on the other side 9. Now I have exactly what we saw way back when in the video on the square root property. All right, I did put up on a video on solving quadratic equations with the square root property. See what I have here? I have a variable inside a square, right? This b is part of the base on this square, and there's no variable outside that square. So remember, in those cases, you can solve a quadratic equation with the square root property. So solve the equation using the square root property, and I'll refresh your memory as to what that is right here. Alright, so what was the square root property? That was the following. It was, if I have some expression squared is equal to some number, right, like I have here, this capital X I just put is like the b plus 1. Right, that's the expression being squared, equals, and then this number, this n over here, is like the number 9. So if you have some expression squared equal to a number, then the values that this expression can take on, right, this capital X, it could be the principal square root of the number, the positive square root or non-negative square root of the number, or it could be the negative square root of that number, and it would be a true statement, right? So that was the square root property. Again, hopefully that rings a bell from just a few videos ago, right, if you've been following along. And then you solve the, so basically you're taking one equation and breaking it up into two simpler equations, 2 degree 1 equations, 2 linear equations, and solving those. And then of course, lastly, as always, check your solutions, back in the original equation. I'll just say check solutions, okay? Alright, so let's do that. Let's use that square root property. Alright, so by the square root property, if b plus 1 squared is equal to 9, that means that b plus 1, could be the positive or the principal square root of 9, or b plus 1 could be, the negative square root of that number 9. Right? And I know sometimes you might see people write b plus 1 equals, plus or minus the square root of 9. I don't know, I don't care for doing that, but you can. Right? I'll write it at the end if we come up with some plus or minus answers. But then look at your radicals here. Right? Look at the roots. What's the square root of 9? Right? The principal square root of 9. That's just 3. So this left equation is b plus 1 equals 3. Or, in this right equation would be b plus 1 equals, the opposite of that, negative 3. Then we solve each of these and get our possible solutions, right? The possible values of b. This one I'd be subtracting 1 from both sides, so we get b equals, 3 minus 1 is 2, or subtracting 1 from both sides of this equation, b equals, negative 4. But don't forget, like I said, to check back in the original equation. Right, so let's go way back. Now I'll just I'll say this one out loud here. I'll just check out loud. How about 2? Put in 2 for b. This is the original equation. 2 squared is 4. 2 times 2 is 4. And we'd have 4 plus 4 is 8. And then you have minus 8 after. 8 minus 8 is indeed 0. So 2 is a good solution. It makes the original statement true. 0 equals 0. And then how about negative 4 for b? Well, negative 4 to the second power, right? Negative 4 times negative 4 would be positive 16. Then 2 times negative 4 would be negative 8. So 16 plus negative 8, which is the same as 16 minus 8, is 8. And then minus 8 again after is 0. That's true. So both of these are valid solutions, right? They are both good. I'll circle them both. So 2 is a solution, negative 4 is a solution, and you might also see, like in a lot of equations or inequalities, you'll see a in some textbooks you'll see them write it out as a set of solutions, right? The solution set, right? So the solution set for this equation is the set, right? Little curly braces with the number 2 in it, comma, and the number negative 4 in it, right? And only those two. Alright, so you might see the solutions written out as a set like that, but I'm not going to do that for future examples. I mean, you can just write, I would totally accept this if I were like grading it or something. Right? Great. But yeah, it's just those steps, right? I'm going to walk through them again here with you. Get it into this form, right? You have your, again, this is for any quadratic equation at all. Get it into this form where you have, the squared term with a coefficient of 1 plus, and then your first powered term, and then everything else on the other side. Then you complete the square, and again, don't forget what you add to this left side, you must also add to the right side. Don't forget it's an equation. Then after adding, you'll have a perfect square trinomial, right? You'll have completed the square, right? Completed the perfect square trinomial. Factor that, right? Write it as a square, like this b plus 1 squared here. And then you solve using the square root property, right? Break up your quadratic equation into 2 separate linear equations and solve those, and of course check your solutions back in the original equation. All right, so let me do that. I have several more examples here. Let's just keep going. Alright, so this next example I'm asked again to solve using the, complete the square method, if you will call it that. Alright, so see I have a z squared now minus 8z plus 9 equals 0. So again, when I'm completing the square, right, I want to get that squared term and that first powered term. So the z squared and this negative 8z, get them on their own side and everything else on the other side. So this positive 9 I don't want, right, if I'm trying to solve this by completing the square. So I'm going to subtract 9 from both sides. That leaves me with z squared minus 8z on the left side equals, and then 0 minus 9 is negative 9 on the right side. Notice that the coefficient of the z squared is 1, so I can complete the square. So now comes that part. So we have z squared minus 8z on the left. I'm going to leave a little space for the other term we're going to add when we complete the square. Equals, and then negative 9 on the right. Completing the square, remember you take the number that's multiplied by the first powered term, right? The coefficient of the first powered term. Take negative 8. What's negative? I'll just do this off to the side. What's negative 8? Cut that in half. That's negative 4. Then square it, right? What's negative 4 squared? That's positive 16. So I'm going to be adding, positive 16. And since I added it to the left, I must also add it to the right. Alright, now that I've done this, right, this addition of 16 gives me a perfect square trinomial on this left side. 3 terms that can be written as a perfect square. Right? So here comes the factoring part. Actually write it as a square. So this is going to be equal, this left side is going to be equal to some quantity squared, some expression to the second power, and that expression is again simply the variable z plus whatever half of that number times the first power was, right? half of negative 8 is negative 4. So the second term in this set of parentheses here is negative 4. And we'll go ahead and double check. Take z minus 4 and square it. Right? Z minus 4 times z minus 4. And do all the distributing and combining like terms. You'll end up with z squared minus 8z plus 16. All right. Then on the other side, negative 9 plus 16 is 7. Right. Wonderful. All right, now comes the square root property, right? Notice I have the perfect conditions for using the square root property. I've got a square alone equal to a number, right? There's a variable inside a square, and there aren't any variables outside that square, right? And the square is alone. So, using the square root property. So by the square root property, and I'm just going to abbreviate this SRP in the future, right, my next couple examples. So by the square root property, this z minus 4, right, the base, could be the positive square root of 7, or this base, this z minus 4, in order for this to be a true statement, could be the negative square root of 7, right? Because either one of these, when you square them, would give you 7. All right, and then we solve each of these, add 4. In both of them, I'll be adding 4 to both sides. So here we have z equals, and then we have the square root of 7, and then plus 4, which is fine to write. It's just typically I like to write a non-radical term before a radical term. So if I add 4, then there will be a positive 4 term on the right side. And then you have this positive, square root of 7 as the next term, right? So my non-radical plus my radical. Again, if you wrote the square root of 7, then plus 4, that's also fine, right? Or this one here, z equals, and again, if I add 4, there will be a positive 4 on the right side. And then I have the negative square root of 7 term, right? And again, these don't go together, right? One's a radical, one's not. They're not like radicals. You can't put them together. And of course, check your solutions. All right. Now this one I'm actually going to do on paper and with the calculator. All right. I'll use a calculator to check as well, just to see, right? Just to really doubly verify. So let's check our solutions. I'm going to do that on this page here. All right. So going back to the original equation, I'll write it again so I don't have to keep shifting the paper back and forth. Here was the original equation. Z squared minus 8z plus 9 equals 0. Now I'm just going to check one of these on paper because again you'll see this is kind of tedious. It's going to take a little bit. But let's plug in, say, this 4 plus the square root of 7 for z. So instead of z squared, I have the quantity 4 plus the square root of 7 squared, then minus 8 times, and then again instead of z, I have this quantity 4 plus the square root of 7, and then plus 9. And is that equal to 0 is what I'm asking. All right, so I'm going to skip a little bit. 4 plus the square root of 7 squared. It's not 16 plus 7, right? You cannot distribute powers. I've mentioned that plenty of times in other videos in the past. You can't distribute powers. This is 4 plus the square root of 7 times 4 plus the square root of 7. And you would do all sorts of distributing. So you'd have a 4 times 4, 16. Then you'd have plus 4 times the square root of 7. So 4 times the square root of 7. And that's after distributing the 4. And then you'd have another 4 times the square root of 7 when you're distributing the square root of 7, and then plus, and then when you have square root of 7 times square root of 7, that's just 7, right? The square root of 49 are just 7. So these 4 terms are what I'm getting when I square this 4 plus the square root of 7. All right. All right. Then the next part, we have this minus 8 times this quantity. You can distribute this. This is when you distribute, right? When you have a number times a sum or a number times a difference, you can distribute there, right? You just can't distribute exponents. So it's negative 32, right? Negative 8 times 4, negative 32 for the next term. And then negative 8 times the square root of 7 for the next term. And then you have plus 9, and then equals 0. And let's see if this ends up being true. All right. Well, let me just go through and look at the like terms. You've got all the non-radicals, all the constants. 16 plus 7, that's 23. Plus 9 would be 32. All right, 16 plus 7 plus 9 would be 32. And look here. Then you have minus 32. So those all disappear. Right? Those all cancel each other, make 0. That's 0. And then look at the radical terms. I've got 4 times the square root of 7 plus another 4 times the square root of 7. That's 8 times the square root of 7. So these make 8 square root of 7. And then look, you have minus 8 square root of 7. So all three of these kind of just get rid of each other. And you're left with 0 on the left equals 0 on the right. Yes, indeed, 4 plus the square root of 7 is a very good solution to this equation. Okay, so you see that can be a little painful to do by hand with these radicals and all that. So what I'm going to do for the other solution when I'm checking is I'm going to use a calculator. All right, even though I know I could do it without one, right? You just saw me do it here, but so let me check the other one. All right, and this might be a bit tiny, but bear with me. So I'm going to replace z with 4 minus the square root of 7 this time. So in parentheses, 4 minus the square root of 7, and then close the parentheses. That's being squared. That's the z squared. Then minus 8 times, and then z again is in parentheses, 4 minus the square root of 7. And then I have then the plus 9. And hopefully this is equal to 0, and look at that, it is. I know, again, it's tiny, but that is equal to 0. So both of these are good solutions. Right? I'll put them in a circle or something. All right. Now, I know some of you have probably seen this, but look at these two solutions. Right? There's 4 plus the square root of 7, 4 minus the square root of 7. They look exactly the same except for that middle sign. So very often you're going to see, maybe these solutions will be written out this way as z equals 4, and then, plus the square root of 7 or minus the square root of 7. You'll see this plus or minus symbol written to indicate that, yes, there are two solutions, one with the plus, one with the minus. So you'll see this pretty often too. Right? Again, I like to split them up myself, but the plus or minus, isn't wrong. Great. All right, so that was just now in those two examples, right? The previous two examples I've done. And you see how in the quadratic equation, you see how the squared term had a coefficient of 1 already, right? I keep saying that the square, in order to complete the square, I want that squared term to have a coefficient of 1. Well, what if it doesn't? Right, let's look at some examples where the squared term doesn't have a coefficient of 1, and we'll see that it's actually very easy to fix that. All right, so here's another one. I'm asked to solve this equation by completing the square. All right. So notice here that the square term does not have a coefficient of 1, and that's a problem. Right, if I want to complete the square later, I need that to be 1. Well, it's very simple to fix that, as I mentioned. Here it's 2 times the square, right? 2 times q squared. Then I have plus 6q, and then minus 1 equals 0. If I want that to be 1, simply divide everything by that number. So all I'm going to do here to fix this is divide by 2, right? Divide by the lead coefficient. Alright, so I'll write that up here. Let's divide by 2, and then the other side, same thing, divided by 2. Now remember, you're doing this to every single term, right? It's like multiplying by a half, right? Dividing by 2 is multiplying by a half, and this is a big sum and difference here. You would distribute the half to all these. You do it to every single term. Alright, so 2q squared, when I divide by 2, would get rid of the 2, giving me q squared, 1q squared, plus, and then 6q divided by 2 would give me, make me 3q, right? 2 goes into 6 3 times. And then negative 1 divided by 2 is just simply negative 1 divided by 2, right? Nothing simplified there. That's negative 1/2. Right. And then on the other side, 0 divided by some non-zero number is 0. 0 divided by 2 is simply 0. Great. So it's very easy to get that coefficient of the square to be 1, right? Just divide by the lead coefficient. Right? Make it into 1. And now I'm performing the same steps I did for the past two examples. I would like the squared term with the coefficient of 1, and then the first powered term, the positive 3q here, I'd like those on their own side. So I'm going to get rid of this negative 1/2, alright? So we're going to add 1/2 to both sides. Alright, leaving me with, q squared plus 3q on the left. And, since the lead coefficient is 1, I'm going to be able to complete the square. So I'm going to leave a little space again so we can, add that new term to make a perfect square trinomial, to complete the square. So I'm going to leave a little space. So 1q squared plus 3q space, and then the other side, 0 plus 1/2, positive 1/2. Alright. Alright, now comes the part where I complete the square. Alright, I've got the q squared plus 3q. Remember how that works? You take the number multiplied by the first power, right? 3 times q, positive 3. I'll do this off to the side. You're going to cut this in half. Well, that's just 3 divided by 2, right? 3/2. If you want to write it as 1.5, fine, but I think it makes it easier to square it when you leave it as a fraction. So here's the coefficient of q cut in half, and then you square that number. Now remember, when you multiply by a fraction, you just multiply the numerators, multiply the denominators. So 3/2 times 3/2 would be 9, right? 3 times 3 in the numerator, over 4, 9/4. Or again, if you want to write it as a decimal, right, that'd be 2.25 or 2 1/4, but I'll leave it as a fraction. So the q squared plus 3q, in order to make a perfect square trinomial, to complete the square, I'm going to be adding this 9/4, right? Half the 3 squared. And I do the same to the other side. Do not forget that this is an equation, right? What you do to one side, you must also do to the other, right? Keep it balanced. Alright. Now, the adding of 9/4 makes this expression on the left side a perfect square trinomial. So it should be able to be factored as such, right? As one expression to the second power, one expression squared. And what that expression is, again, is just the variable q plus whatever the second term in here is whatever half of that number times the first power was. So half of 3 was, positive 3/2. And again, double check. Take q plus 3/2 and multiply it by q plus 3/2. Do all the distributing and combining like terms, and you will indeed see that you get q squared plus 3q plus 9/4 back. Great. Now this other side, look at, I'm adding fractions. Remember, you need a common denominator when you add two fractions. So I'm going to do this over here. What's the least common multiple of 2 and 4? That's just 4. So I would multiply this first fraction by what? 2 over 2 to get a denominator of 4. That's 2/4, right? Same as a half, plus the 9/4. Right? And then when you have that common denominator, right, that sticks around when you add them, so I keep a denominator of 4, and you only combine the numerators. 2 plus 9, 11, right? So I'm getting here q plus 3/2, that quantity squared, is equal to 11/4. And now I have it set up to where I can use that square root property, right? There's a variable inside a square. no variable outside that square. I'm not seeing q anywhere outside the square. And the square is isolated. The square is alone, and you have some number on the other side. So, by that square root property, this base, right, the q plus 3/2, could be equal to the the positive square root, or the principal square root of 11/4. Right, again, make sure this is all underneath the root. Okay, it's all inside the radical. Or this base, this q plus 3/2 that's being squared there, could be equal to the negative square root of 11/4. Right. And then of course we're going to want to simplify our radicals. Remember that we don't like radicals over denominators. Right. Now, if you recall a little, fraction property, quotient property for radicals involving real numbers here, this is, you can take the square root of the numerator and the square root of the denominator separately. So this is q plus 3/2 equals, and then this, you can simplify this as the square root of 11 in the numerator, and then, big division sign, and, again, make the bar long enough so I know it's not in that first radical. And then what's the square root of the denominator? The principal square root of 4 is 2. So numerator square root of 11, denominator 2. Or, and the same thing over here, q plus 3/2 equals, the opposite of that, right? Negative. And then this square root of 11/4 is, again, this square root of 11 in the numerator divided by big division sign, and then the square root of 4, or just 2 in the denominator. Alright, and finally, I would be subtracting 3/2 from both sides. Alright, same for this equation over here. To get q alone, right, subtract 3/2. And, we have on the left side q equals these two fractions where I'm subtracting them. They have the same denominator, right? They already have a denominator of 2, so that's going to stay the denominator, right? Like I mentioned earlier, the common denominator doesn't change. And I'm only combining the numerator, so I have, the square. Now you can write the square root of 11, then minus 3, right? I can write the square root of 11, then minus 3 up in the numerator here. But as I mentioned in the earlier example, typically you'll see written a non-radical term first, plus then the radical term. So the square root of 11 minus 3, sure, that's fine, but you can also rewrite it as, the minus 3, the negative 3 term first, and then the positive square root of 11. So very often you'll see it written this way instead. All right. So there's one possible solution. Again, we're going to check that. Or, and then again, same thing, I subtracted 3/2 on both sides of this equation. We're getting q equals, and then over here, again, we have this fraction, and minus 3/2 minus another fraction. They have the same denominator already. That denominator is 2. And then the numerators are, you have negative square root of 11 minus 3, which again, you wouldn't be wrong to write that. Negative square root of 11 and then minus 3. But as I've said already, most times they'll put a non-radical term before a radical term. Alright, so put the negative 3 first, and then the term, the radical term, negative square root of 11. So negative 3 minus the square root of 11, all in the numerator. All right, and let's check these. Like I said, it would be kind of a little bit annoying to check this by hand. All right, let me go back. Here's the original equation. All right, and I'm going to use a very cool feature on my calculator. I mean, I know a lot of calculators do have something like this, where I can save a value and just keep reusing it as a letter, use it over and over again. Alright, so I want to check this number. Alright, I want to check, is negative 3 plus the square root of 11, all that divided by 2, is that a good solution to my original equation here? Here's the way it originally looked, right? 2q squared plus 6q minus 1 equals 0. Alright, so on my calculator, I'm going to enter this number, okay? So here's a cool feature about, a lot of, this is my graphing calculator. I know a lot of other calculators do this as well. I take, in parentheses, the whole numerator in parentheses because it's got multiple terms, -3 plus the square root of 11, and then, close parentheses, then divide that by 2. All right, so here's a number, it's 0.15831233952, and this calculator here has a button that has STO on it, meaning store. I can store my previous answer. All right, so it'll take my previous answer and store it as whatever I want. And since it's the letter Q here, I'm just going to use the letter Q. All right. So there are letters all over this, and you can use the alpha key to enter your letters. I hit enter when I enter the Q. So now whenever the letter Q comes up, whenever I enter the letter Q, it's going to be this -3 plus the square root of 11 divided by 2 of this 0.15831233952. Alright, so pop in that, let's plug that into our equation up here. So on the left, let's plug in the left side here. I have 2 times, and then, again, Q squared, right? And remember, every time I see Q, it's this number. I'm checking this number. Then we have plus, and then 6 times, and again, I'm going to use my Q, this number, and then -1. And look, that is indeed 0, right? I'd have 0 equals 0. This number works. And you can do the same for the other one, and I promise you it'll work as well, right, if I did everything correctly. So both of these are valid solutions. I'm going to circle them both. And as with the last example, you notice how very, very similar these look. This is -3 plus the square root of 11 all over 2. This is -3 minus the square root of 11 all over 2. So very often you'll just see them written kind of on the same line. You might see them written this way, Q equals, -3, and then you have one with the plus, one with the minus, right? So plus or minus the square root of 11, and then, all of that over 2, right? So again, remember, this means 2 solutions, right? One with the plus, one with the minus, -3 plus the square root of 11 over 2, -3 minus the square root of 11 over 2. Right, and you'll see this, very often. All right, so I've got one final example, right, where I'm doing the same stuff, right? And notice how, the first example I did had some rational solutions. The last couple ones had some irrational solutions. And as I mentioned at the beginning of the video, you can use this complete the square method to solve any quadratic equation. All right, so that's the beauty of it. All right, so this last one, I have 3m squared plus 2m plus 7 equals 0. All right. So again, the first thing I'm noticing, I'm trying to solve this quadratic by completing the square, and the coefficient on the squared term, right, the m squared, is not 1. So all I'm going to do to simply fix that is divide by it, right? If I want to make 3 into 1, just divide everything by 3. All right, so I'm not going to write that division by 3 out. I'm just going to write what the final result is going to be. So when I divide the first term by 3, the 3 will cancel. I have m squared. 1m squared, like I want. Next term, plus 2m divided by 3. Well, 2 divided by 3 is simply that. It's 2/3 times m to the first, right? Instead of 2m to the first, I'm dividing by 3. And then the next term, plus 7 divided by 3 is again exactly that. That doesn't simplify any further. So 7 divided by 3 are 7/3 equals, and then the other side, 0 divided by 3, 0 divided by any non-zero number is 0 again. All right, great. So now I have what I want, the coefficient of 1 on the m squared. I'd like to complete the square, so get this m squared and m to the first term on their own side. All right, so I'm going to get rid of this positive 7/3. Right? I'm going to take away the fraction 7/3 from both sides. All right, that leaves me with m squared plus 2/3 times m. And then just as before, because this square term has a coefficient of 1, I can complete the square. We're going to be adding something to this to make a perfect square trinomial. So I'm going to leave a little space, equals, and then over here 0 minus 7/3 is negative 7/3. All right. Now to complete the square part, remember how this works again. You take the coefficient, the number times the first power, right? This is positive 2/3, and then you cut that in half, divide it by 2. All right, so take 2/3, divide it by 2. Well, remember what it means to divide by 2. It means take 2/3, and instead of dividing by 2, you multiply by a half, right? Remember, division is just multiplication by the reciprocal. So dividing by 2 is the same as multiplying by a half. And this is 2 over 6, which is 1/3. The 2's would cancel, and you have 1/3. And then you take that number, right? So that you take the 2/3, cut it in half, you get 1/3, and then square it. 1/3 squared would be 1/9, right? 1 times 1 over 3 times 3. So to both sides, I'm adding 1/9. All right, so I'm adding 1/9, and don't forget it's an equation, right? You got to do it to both sides, keep it balanced. And then the addition of this 1/9 creates a perfect square trinomial. This m squared plus 2/3 m plus 1/9 is, a perfect square trinomial. It should be able to be factored as the same factor twice. So, and what are those factors? Right? So I can write m squared plus 2/3 m plus 1/9 as, some expressions squared. Remember how this is built, right? The expression is simply the variable for the first term in here, plus whatever half of that number times the first power was. Half of 2/3 is positive 1/3. And go ahead and try it out. Check it out. Take m plus 1/3, multiply it by m plus 1/3 again. Do all the distributing and combine some like terms. You're going to see that this is indeed equal to m squared plus 2/3 m plus 1/9. Alright, and the other side, just as with the last example, I can't put these together right now. Negative 7/3 plus 1/9, when you add or subtract, you need the same denominator. So what's the least common multiple of the denominators? 3 and 9, that'd be 9. So I'll leave the 1/9 the way it is. I would multiply this fraction by 3 over 3, right, to get a denominator of 9. So I'm going to take this up here. Sorry about the clutter, but this would be what? Negative 21/9, right? 7 times 3 over 3 times 3, plus 1/9. And now I have a common denominator, all right? And when you have a common denominator, that denominator stays. So I still have a denominator of 9. And then you just add the numerators. Negative 21 plus 1 would be negative 20, all right? So here I have a situation where I can use that, square root property. I have a perfect square all by itself equal to some number. There's a variable inside a square, no variable outside the square. So let's do that. Okay, so by that square root property, this base, right, so I'll write that again. Here we go. So by the square root property, SRP, this base, this m plus 1/3, could be equal to the principal square root, or the non-negative or positive square root of this number, negative 20/9, or the base m plus 1/3 could be equal to the negative square root of this negative 20/9. And look, we have the square roots of negative numbers. These are not real answers, right? And I've mentioned this in other videos, again, if you've been watching, you've heard me say this before. When you see the square roots of negative numbers, you should automatically think, or immediately think, I need to rewrite this as a pure imaginary number, a number involving that imaginary unit I. Right? Remember, I is that square root of negative 1. Right? So immediately I'm going to do that. Right? So we have m plus 1/3 equals, and remember how that's written, the square root of negative numbers if I want to write it as a pure imaginary, a real number times I write it as the square root of the positive. The square root of positive 29ths, that's a real number, the square root of a positive, times I. And if you're writing it the way I am here, make sure the I, if it comes after, make sure the I is not in the square root, right? The I is not part of the radical. Don't make the bar too big. So very often, instead of doing the I after, they'll put the I before, I times then the square root of positive 29ths, right? And I'll do that over here as well, right? Or we have m plus 1/3 equals, and then the opposite of that, so negative, and then I times the square root of 29ths. Right. Now, got these two equations, right? M plus 1/3 equals I times the square root of 29ths. M plus 1/3 equals negative I times the square root of 29ths. I'd like to now simplify these radicals. Right, the square root of 29ths, and I'm going to do that on a separate page and come back. Right. So the square root of 29ths. Remember that fraction property when I'm dealing with real numbers, right? This is a real number now. I can write the square root of the numerator, right? The square root of 20, and then big division there. So, make sure it's not in the radical, and then this is divided by the square root of 9, and the square root of 9 is 3. Right? The principal square root of 9 is 3. Square root of 20. Remember, I can break that up to the square root of 4, right, which is a perfect square, 2 squared, times the square root of 5. The square root of 4 is 2, times the square root of 5 is just the square root of 5. So this would be considered the simplified radical, right? There's no radical in the denominator, right? It has a rationalized denominator, and the radical in the numerator simplified, right? There's no perfect square other than 1 that goes into 5 evenly. All right, so I'm going to keep that in mind, and we're going to rewrite our equations. Right? So we have m plus 1/3 could be equal to, I times this, which will put I in the numerator. Right? This is like I over 1. Anytime there's not a denominator, you can think of it as 1. So I'm just going to put this factor of I in the numerator with this 2 in the square root of 5. So that's 2 times I times the square root of 5 in the numerator over 3. Right, so this number here is exactly the same as I times the square root of 29ths. All right, the 2 times I times the square root of 5 all over 3. Right. Or the m plus 1/3 could be equal to the opposite of this, right? So negative 2 times I times the square root of 5 all over 3. Right. Great, so we're almost done. Now I want m alone, right? Solve for m. So I would just need to subtract 1/3 from both sides of both of these equations. Okay. So in the left equation, I've got m equals, we're subtracting two fractions, right? I got a fraction and then minus 1/3 another fraction. They have the same denominator already, right? They both have this denominator of 3. So the result will have a denominator of 3. And then you combine the numerators. So I have 2 times I times the square root of 5, that, and then minus 1. And you can write that if you want. 2I root 5 minus 1, and leave it that way. But as before with radicals, usually they put the real number the real number first and then the imaginary. So instead of 2I root 5 times the square root of 5 minus 1, I'll put the real number term, the non-imaginary, the real number term first, negative 1, and then the imaginary term, which is positive, 2I times the square root of 5 there. And again, all of that is in the numerator. Or same thing over here, m equals, and then same thing, these two fractions that I'm adding or subtracting here have the same denominator of 3, so the result will have a denominator of 3. And you can write the numerator as -2i times the square root of 5 and then -1. But as I mentioned, typically they put the real numbers first and then the imaginary terms after. So -1 first and then the imaginary term, the -2 times I times the square root of 5. And all of that in the numerator. Alright. Now checking this is a bit more difficult. Now you can do it by hand. Right? I can plug these numbers in to my original equation, which was this way up here. Right? 3m squared plus 2m plus 7 equals 0. I can plug one of these in for m and multiply it out and do all sorts of foiling, and also remember, whenever you see I squared, that's -1. So if you could do that by hand and see that indeed these are both good. But I wanted to show you one more thing on the this is a TI-84, alright, and again, it's going to be tiny. I'll just say things out loud and point them out to you. Hopefully you can see on your own calculator more clearly. You can actually enter imaginary numbers in your most graphing calculators. Again, this is just an 84. TI-83 would be similar. If you hit the mode button, there's one in the top row that says mode. You hit the mode button, and then further down there's a little line where it says real, and next to it says A plus BI. If you click on that, have the A plus BI thing flashing. Enter that and get out. Now you can enter imaginary numbers and it won't give you an error. If you leave it in the real mode and try to enter imaginary numbers or square roots of negatives, an error will come up saying that the number is not real. Alright, so I can enter a number like this on parentheses in the numerator. Let's try this one here, the -1 plus 2 times I times the square root of 5 and then all divided by 3. So I'll put the numerator in, -1 plus and then 2 times I. Now the I is above the decimal point on this. It's in blue on my calculator, so I'd have to hit the second button, then the decimal point for the letter I to show up. The number I, that's actually the square root of -1, times the square root of 5. Alright, that's all in parentheses, that's the numerator of this, and then divided by 3. Alright, and you see some crazy thing come up. Now again, I'm going to store this like I did in earlier example. I hit STO. I'm going to store this number as the letter M, alpha M, which should be is in green. Alright, so every time I see the letter M, it's actually this number when I'm testing it right now. And again, I could have M be this other number. Right? I could do this one instead. But right now I'm having M represent this number, right? This complex number with an imaginary part. Alright, so back in the original equation, I have 3 times, and then I'm plugging this number, the number I had, in for m squared, this number here. And that's just, m squared. Alright, then plus 2 times, I'm going to use the letter m again. Again, every time I see m, it's that number. And then plus 7, and hopefully I get 0. And yes, I do. And it works. Alright, it does work. It makes that a true statement. And you can do the same thing with a calculator, or again do it by hand, right? Just lots of foiling, lots of distributing you'd have to do by hand. It'd be a little annoying, but you could still see that this number would also work. Alright, so I'm going to circle both of them. These are both good solutions. And of course, you could always write the solutions this way too. M equals, you see how they're exactly the same except for this sign. There's a plus here, minus there. So both of them have this -1, but then you have your plus or minus, right? So plus or minus, and then the 2 times I times the square root of 5, and then all of that, right, divided by 3. You could write them out this way as well. Wonderful. Alright, so that was a lot, I know, but it's very, very nice, because you can use this method I've been showing you to solve any quadratic equation, right? You saw my first example had rational solutions. My next 2 examples had irrational solutions. My last example, this one here, had a solution that had an imaginary part to it. It covers all the complex numbers. Every quadratic equation you can think of, can be solved by this complete the square method. Right. Now sure, there are sometimes it might be more efficient to solve by factoring, or just use the square root property and not need to complete the square. So if you recognize that you can do that, go ahead and do that. But if you forget how, or you just say, hey, you just don't want to do too much thinking about it, and this is the only tool you'll need, is completing the square. Great. Alright, so as I like to say also at the end of these videos, do the best you can to learn the material on your own before you go looking for help. I have found over the years that people who take the time and the effort to learn something on their own, usually remember that material for longer, and they remember it better and are more proud of themselves. So of course, read the material, right? Read through the author's examples. Perhaps even try to work out the solutions to some of the author's examples before you read how the author did it, and then compare your work with the author's. Read it later and then see how you compare. See if you can learn from some mistakes there. Obviously, work on tons of exercises, practice problems. Look for solutions to those whenever they're made available. To check yourself, track your progress. Just don't forget, that practice makes progress, right? The more you practice something, the better you should be getting at it, hopefully, right? And don't just give up on an exercise or a problem just after one attempt or two attempts. Don't give up so easily. Very often in mathematics there are several approaches that'll work for any particular problem. So if after several approaches at a problem, you're still not getting it, still not seeing how to do it, maybe you should go back and read the material again, maybe even a third time. Because if you've been working on some problems, there's a good chance you have a better idea as to what the author wants from you, what the author expects of you. So when you go back and read the material again, or even at that third time, you'll have a better idea as to what to look out for in the reading, what's important, and maybe some things will pop out at you that didn't the first time through, and it'll make working on the problems that much easier. But if after that, if after several read-throughs of the material and several attempts at problems you're still not getting it, perhaps that would be the time to ask for help. And it is not a sign of weakness whatsoever to ask for help. That is what other people are there for, right? To help you. So ask a teacher, a tutor, a friend, someone in your class who knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online. There's tons of those too. Videos like this one, or plenty of other ones out there that are better than this one. I assure you they're out there and they're easy to find. But just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is the hardest thing for most people, stay positive. Right? Try to have fun with it. Make a game of it. Believe in your abilities. Right? Believe in your ability to work through struggles and work through failure and work through mistakes and fix them. Don't get so easily frustrated. Work through that frustration. Maybe take a break now and again to take a breather, relax, but go back and try to have that positive mindset that you're going to make it through. It's those times of failure and struggle and mistake that you can learn the most, and learn the most deeply. Because if you persist and fix your mistakes, you learn how to fix your mistakes and work through the struggle, you'll remember that material far longer and far better than someone who just got it right the first time and breezed through it and wouldn't give it a second thought later. And those people usually will forget something like that, something they breeze through. They'll forget it in a week. But if you work through and struggled and made the effort to fix it, you'll probably remember that for months on end, maybe even longer, if it was that if there was that much emotion tied to it. Okay, so stay persistent, keep practicing, stay positive, and don't give up. And I just know you'll get it. and thank you very much for watching.